In today's video, we are going to look at concavity. This is an analysis of the second derivative. In this video, we're going to define what we mean by concavity, as well as state the concavity test. And we will also look at the second derivative test, which is another test for relative extrema. So let's start by looking at a couple graphs. Let's look here. Consider this graph right here. So we say that this graph is concave up or concave upward. Right, and what we want to do is let's look at the tangent lines. So we can have maybe this. Here's a tangent line, right? There's a tangent line. Maybe right here. Obviously, we're going to have a 0, right? Slope of 0. Then we're going to have something like this. Maybe that. Something along those lines, right? But notice as we move left to right what's happening. The slopes of the tangent lines are increasing. But since the slope of a tangent line is just the derivative, this means that f prime is increasing. Right? Now, f prime is a function. So we could also say, since f prime is increasing, f double prime is greater than 0, right? Because f double prime is the derivative of f prime. Well, if we look at another graph, let's look one that's concave downwards now. That kind of graph will look like this. Right? This is concave down or concave downward. And again, we want to analyze tangent lines. We're going to have that. Of course, we're going to have a horizontal line, right? But then we'll do maybe one there, and one there. And you get the picture. In all of these cases, as we move left to right, the slopes are decreasing, which means that f prime is decreasing, or f double prime is less than 0 for the same reason as when we looked at the increasing case. Well, this gives us a definition for concavity then. Let f be a function that is differentiable over an open interval I if f prime is increasing over I, we say that F is concave up over I. Concave down has almost an identical definition. Except here we say if f prime is decreasing over I, we say that f is concave down over I. Now, as we saw up here, we can also say we're concave up if f double prime is positive, and concave down if f double prime is negative. This is actually our test for concavity, which is essentially an increasing-decreasing test on f prime. Right? So we're going to formally state it now. So we say, let f be a function that is twice differentiable over an interval I. First, if f double prime is greater than 0 for all x in I, then f is concave up over I. If f double prime is less than 0 for all x in I, then f is concave down over I. And the proof of this is it just follows directly from the test for increasing and decreasing. Right? If f double prime is greater than 0, then by the test for increasing and decreasing, f prime is increasing over that interval, which then by definition means f is concave up over that interval. And similarly for if f double prime is less than 0. Now, we noticed that the function would switch from increasing to decreasing at a point known as a critical point. The question is there a similar point for concavity? Right? So is there a point where it switches concavity? And the answer is obviously yes. If it's going to switch concavity, it does so at a specific point. Specifically, it's going to do so when f double prime is 0. Right? Well, we call the point where a function switches concavity a point of inflection. So if f is continuous at a point I, and f changes concavity at I, then the point I f of I is an inflection point or a point of inflection of f. Notice here, I must be within the domain of f to be a point of inflection. So if concavity is switching at a vertical asymptote, that is not a point of inflection, right? Because f of I is undefined. We now take a look at the second derivative test, which is another test for extrema. And this can easily be seen, again, by looking at these graphs, right? This point here it's not really showing up. Let's do this. So this point right here would be a relative minimum, right? It switches from decreasing to increasing, and that means it's concave up. So f double prime would be larger than 0. This point over here would be a relative max, right? Function goes from increasing to decreasing. Well, that is concave down, right? Meaning f double prime would be less than 0. That is our second derivative test. Suppose that f prime of c is equal to 0 and f double prime is continuous over an interval containing c. If f double prime is greater than 0, then f of c is a relative minimum. If f double prime is less than 0, then f of c is a relative maximum. If f double prime I need to make adjustments. These should be f double prime of c's. All right, so if f double prime of c is greater than 0, it's a relative min. Sorry. If f double prime of c is less than 0, then it's a relative maximum. If f double prime of c is equal to 0, then the test is inconclusive. Meaning f of c could be a relative max, a relative min, or neither. Right, at which point you'd have to go back to the first derivative test. All right, so proof of the first statement. Since f double prime of c is larger than 0, and f double prime of x is continuous over an interval I containing c, f prime of x is increasing over I. Since f prime of c equals 0 for all x in I, f prime of x must be larger than 0 for x less than c, and f prime of x, I said less than 0 here and wrote greater than, and f prime of x is greater than 0 for x greater than c. So f has a relative min at x equals c by the first derivative test. I'll call it f dt. All right, that proves the first statement. Second statement is a very similar proof. All right, since f double prime of c is less than 0 and f double prime of x is continuous over an interval I containing c, we can say that f prime of x is decreasing over I. Since f prime of c is equal to 0 for all x and I, we must have that f prime of x is larger than 0 for x less than c, and f prime of x is less than 0 for x greater than c. So f has a relative max at x equals c by the first derivative test. Statement number 3 is going to be left to the viewer. The functions x cubed, x to the fourth, and negative x to the fourth will show that if f double prime of c is equal to 0, then c could result in a minimum, a maximum, or neither. And it is left to the viewer to actually do the work on that. And so that completes the proof of the second derivative test. And as always, we will finish up by looking at a few examples. We're going to look at this function here. And we will determine intervals of concavity as well as listing all the points of inflection. All right, so the first thing we need to do, take the first derivative. That is 3x squared minus 6x minus 9. Now we take the second derivative. Set that equal to 0. Right, there's nowhere that's undefined, so we'll set it equal to 0 and solve. This would give us x is equal to 1. And now we proceed in much the same way. We want to set up our test intervals, and then we want to test the sign now of f double prime for each of those intervals. Right, so we'll go negative infinity to 1, 1 to infinity, right? Again, what we're doing is we're splitting up the domain of f at all of these points right here. 0 is in this first interval, and we find that f double prime will be negative at that point. If we plug in 2, we find that f double prime will be positive. So we are concave up over 1 to infinity, and we are concave down over negative infinity to 1. Our inflection point will be when x is equal to 1. Right, so you just plug 1 in back up here, and we get f of 1 is negative 12. And this is actually a complete analysis of the second derivative. Second example, we're going to do the same thing, except on the function x to the 1/3 minus 5x to the 5/3. F prime, you get 1/3 x to the negative 2/3 minus 1/3 x to the 2/3. Right? So now we take the second derivative. We'll get negative 2/9 x to the minus 5/3 minus 2/9 x to the minus 1/3. Right now, if we simplify this, we'll have negative 2 over 9 x to the 5/3 minus 2 over 9 x to the 1/3. Common denominator is x to the 5/3. Right, that means we're going to have negative 2 minus 2x to the 4/3 all over 9x to the 5/3. I factor out that negative so we can have 2 plus 2x to the 4/3 over 9x to the 5/3. Now, f double prime of x is undefined at x equals 0, so there is a possible inflection point. Will f double prime ever equal 0? This would mean that 2 plus 2x to the 4/3 is 0, which means x to the 4/3 would have to be minus 1. But since x is being raised to a 4th power, right, we have cube root of x all to the 4th. That is not possible. All right, so that has no solution. So we split up our domain at 0, right? And the domain is, of course, all real numbers. If we take a negative number, Numerator will always be positive because we have a fourth power. So this will be positive, positive plus positive. Right, the denominator here will be negative, and that's being multiplied by a negative, so this is positive. Now if we take a positive number, it'll become negative. So we are concave up over negative infinity to 0. We are concave down over 0 to infinity. And we have an inflection point at the point 0, and we plug 0 back in, we get 0. As our final example, we will be using the second derivative test to find extrema of the function x to the fifth minus 5x cubed. And so the first thing we have to do is find all points where f prime is equal to 0. 5x to the fourth minus 15x squared. We can factor out a 5x squared and be left with x squared minus 3. Set that equal to 0. This means that x is 0, or x is plus or minus root 3. Take the second derivative now. So we get 20x cubed minus 30x. Now we want to test each of these points. F double prime of negative root 3. Right, this will become negative 60 root 3. This is positive 30 root 3. This will result in this being negative. Right, this means that f of negative root 3 results in a min. I'm sorry, in a max, not a min. I shouldn't say results in because I'm saying f of negative root 3 is a max. If we take a look at f double prime of 0, that'll give us 0. This means that the test is inconclusive. If we take a look at f double prime of root 3, we'll get something greater than 0, which means that f of root 3 is a min. Now for this video, I'm not going to try and use the first derivative test. The point here is just to get a look at the second derivative test. Right, but normally what we would do is we would then look at the first derivative test here to determine whether 0 is a min, max, or neither. And that concludes this video on concavity. The next video in the series will be taking a look at combining the last two videos as well as knowledge of pre-calc on functions to go ahead and sketch the curve of any function without the aid of technology. So I will see you all in the next video.